continuing from what we did in class today, we're going to want to show you how to solve a problem here for a mass spectrometer. You're given only the strength of the electric field, the strength of the magnetic field, all right, and the distance on the photographic plate from the entrance that each particle lands. And you've been asked to determine the mass of each of these two atoms, okay? And the question then goes on to say, what can you conclude from this difference, okay? And conclusions down at the bottom, okay, is that we have different mass values there. But anyways, let's get into this though, and talk about how we get to that conclusion. So first of all, in order for us to be able to determine, let's see, we have the strength of the electric field. In order for us to be able to determine the mass of these two particles, all right, we have to be able to find how fast they're moving. Now, the speed at which they should move is going to depend on the ratio of the strengths of these two fields. All right. So remember from class, I showed that the strength of, that the velocity is going to be the ratio of the electric field to the magnetic field. So when you solve for that, it's just going to be, let's see here, 6.67 times 10 to the 5th meters per second. All right. So we have these two carbon atoms. All right, they'll be singly ionized. And what happens once they've been sent to this speed, somehow they've been accelerated up to that speed, they go through the magnetic field and they curve, and these are the two distances at which they land from the entrance. Okay, so if they come in at this speed, all right, that means the mass of one of these. Okay, and just to note too, because this is the distance, all right. If we go back to the image that's up here, it's this total distance right here. Okay, we need to take half that for the radius. All right. So when we solve for the first one, with the radius being equal to 0.098 meters, all right, that's half of 19.6 centimeters, we get the following. I showed this derivation in class for how to solve for the mass. Okay, this is the equation that we'll be using. And substitute all of our values in. We end up with 1.998 times 10 to the negative 26 kilograms, and then we do the same thing for the mass of our other atom. Okay, and we do that here. Let's see, we end up with, this is at a different radius. This radius instead is 0.106 meters. Okay, this mass would be 2.16 times 10 to the negative 26 kilograms. Now, the missing piece of information that you don't have, I believe, would be the charge. And since they're singly ionized, each has a positive charge of just one fundamental charge. Okay, positive 1.6 times 10 to the negative 19 coulombs. All right, so that's the big idea there for that type of a problem. And really, you're just going to have to be looking at these different equations that we did in class, and that's it for the mass spectrometer. And understanding the the physics behind how the velocity is chosen and why the fact that it curves in the field, magnetic field, and comes back and hits a photographic plate. So what this tells us is that we have the same nuclei, carbon, in terms of number of protons, but obviously we have different mass values for each of those protons. So our conclusion here, what this difference tells us is that we have evidence for the existence of isotopes. All right, seeing these results. Okay, so overall, now if you skip back to the end of half-life, all right, you'll find this chart. These are 5 different items here, features of the atom that you need to be familiar with. And so far, we've covered everything except for nuclear energy levels, which we're going to get to in a little bit. But each of these, all right, tells us something. We have evidence for why we have this nuclear model of the atom, and we finished quantum physics. All right, we explained why those the Bohr model didn't work with the orbits like planets. We talked about isotopes using a mass spec, right, for this, and then as well, in addition to that, nuclear masses, okay, being able to be measured with a mass spectrometer as well, okay, and the Geiger-Marson experiment is a big thing here for understanding the fact that the atom has a nucleus. All right. So understanding all those different evidences for how we know what we know about nuclear physics is required for this chapter. Now, let's talk about what exactly is happening in this nucleus. There are 4 forces in nature. You need to be familiar with all of these. We've studied the gravitational and electromagnetic force at length. 2 forces we have not touched are the strong nuclear force and the weak nuclear force. We won't get into the weak nuclear force because it deals with beta decay. It's something that is just beyond the scope of this course. But I do want to talk about the strong nuclear force. All right. Let's think about really quickly. Okay, the fact that a nucleus is made up of just a bunch of positive charge. So how is it that all this positive charge isn't blowing the nucleus apart? Well, it turns out that there's another force that exists between nucleons, okay, any 2 nucleons, neutrons and protons, and that force is attractive and very strong, but it only acts at a very, very short range, 10 to the negative 15 meters. So that's the only place that we see it. So that's why, at such a short range with all those neutrons, protons really, really close together, like a bunch of hooks, you can think of it. The strong nuclear force hooks into all these neighboring nucleons and holds it all together, and is able to overcome that electrostatic repulsion. Okay, so neutrons play a big role in keeping nuclei stable. We have a graph right here, this nuclear stability plot. All right, it's what's called a Sager plot, and I don't know if I'm saying that last name right. But what we see here, all these little dots are all the different known isotopes. And you see that on this line where the number of neutrons equals the number of protons, we have a departure as we get up into the higher elements on the periodic table according to atomic number, that it skews over here so that there are more neutrons than protons. And the reason for that is that you need more neutrons to help keep everything together. Okay, there's a few paragraphs written in your packet there that you can read about that. So these are a couple of important graphs, this idea of binding energy. Okay, and I'm going to come back to this here in a little bit. First of all, though, here's a bigger version of that nuclear stability plot. If you want to draw something like this, that would be good. This again just helps you to see that there are more neutrons in the isotopes that exist than there are protons in general. Okay, so it turns out, okay, that atoms, okay, in general, nuclei in general, okay, have something what's called a binding energy. So what holds them together? So if you consider simply just an atom, okay, of carbon, and the fact that it has, we'll say carbon-12, 6 protons and 6 neutrons. If you're somehow able to find the mass of those single protons and neutrons and add them all up, that mass will be more than just the mass of the nucleus itself. In fact, there's mass that goes missing, and that missing mass is mass that we consider to have been purely converted to energy through the process of nuclear fusion. All right. We're going to explain this a little bit more, but the idea is that energy is what we call binding energy. Okay, it's the energy that has been released so that these nucleons can stick together. And this comes with a wild idea, all right, that mass and energy are equivalent, which comes from special relativity from Einstein. So we're going to talk about this more and more as we get to these sections. But let's just start off with this idea of binding energy right now. And let's put it in the context of this binding energy per nucleon, okay? And so we're going to come back to this after we formally define it, but just as in general, just describing these things, okay? As a nucleus gains more nucleons, its total binding energy, okay, is going to increase, while its binding energy per nucleon will also increase, okay? So this is the total binding energy, all right, to keep it together. But the binding energy per nucleon is going to increase until iron and nickel, okay, and then it begins to taper off. And what this tells us, right, is that iron and nickel are the most stable elements. Okay. So anyways, most nuclei have a binding energy per nucleon of around 8 mega electron volts. Okay. So given that, estimate the total binding energy of an oxygen 16 nucleus. So if each nucleon is going to give up 8 mega electron volts, all right, when it's binding together, 16 times 8 tells us, all right, it's approximately 128 mega electron volts. Okay, so as the binding energy per nucleon increases, the nucleus is more stable. Okay, so for each of these nucleons to have achieved this configuration, it's given off more energy. It's at a lower energy state, if you want to think of it like that, and that is more stable. Okay, so nuclear reactions, both artificial and natural. Okay, I'm going to describe both of these processes. Occur only if they increase the binding energy per nucleon ratio. In other words, if they make it more stable. Okay, so this graph up here, all right, it's going to look something like this, but what we have here is we have a place nucleon number here. Right? This is the total number of nucleons, or the mass number. Okay, so the lower mass numbers, okay, we have the processes of fusion that happen here, and in the higher mass numbers we have the process of fission. All right, a different nuclear process, and we're going to explain what these are in a little bit. All right, but it's this idea that they're both going towards a more stable configuration. Okay, eventually, and that most stable configuration, the most stable elements are iron and nickel. All right, so this is just introducing here the idea that the nucleus has some interesting features. Okay. With a strong nuclear force and the fact that there's missing mass. All right, I just kind of want to introduce that right now, and in the next video I'm going to give a more formal definition to this idea of binding energy, and we're going to do some problems with that.